Hello, my name is David, and today I'll be talking about reward increment equals non-negative factor by offset reinforcement by characteristic eligibility, or as Ronald J. Williams, the creator of this algorithm, wrote more succinctly in his 1992 paper, the reinforce algorithm. This algorithm is the foundation of all policy gradient reinforcement learning, and in fact, I would say the baseline for all deep reinforcement learning that's policy-based. There's a lot of information that needs to be covered before we get into the algorithm itself, so we'll start from the very beginning. What is reinforcement learning, anyways? Reinforcement learning is a machine learning method that focuses on optimizing the way an agent interacts with a given environment to complete a particular task. The agent interacts with the environment through an action, setting the environment into a particular state, and receiving a reward based on how good this action is. There's a way to formalize these definitions, which is typically done through the Markov decision process. This is the framework that's used to model the problems reinforcement learning seeks to solve, and it can be boiled down to this quintuple here. S is representative of all the possible configurations the environment can be in, or states. A is the set of all possible actions your agent can take. Each time the state changes, the agent picks its next action based on our policy pi. For now, we can see a policy as a sort of map for a state to an action. This represents the behavior of our agent, and this is what we are trying to learn. P is our state transition function, so the probability of a particular action being taken given a certain state. R is the scalar reward for taking an action, so how good an action is. And gamma is our discount factor. This is the importance of future rewards. So the higher gamma is, the more an algorithm values our future rewards. The Markov decision process is, well, a process, and it can be displayed as this. So at each time step, the agent observes our current state, picks an action based on that policy, receives a reward, so how good that action was, and moves on to the next state. And this is done until the episode, or our trajectory, tau, is complete. And the trajectory only completes when either the task is done or the agent fails to complete the task. So to put it into a practical perspective, let's say in the case of a self-driving vehicle, the trajectory is complete either when the vehicle makes it to its destination or is rendered inoperable. That is what tau is. Now, this trajectory's cumulative reward can be represented by these two equations. On the left, we have the discounted cumulative reward based on a time step k. So this changes based on where we are in our trajectory. On the right, r of t is assuming that the trajectory begins at state 0. So this is the sum of our entire reward. But that does beg the question, what is a reward? Rewards can be sort of estimated using something called the value function. The top one is our state value function, so it outputs how good a particular state is to be in, and the bottom function is our action value function, or Q function, which tells us, given a particular state, how good is this action to take. Now, these representations are very good for helping us define what goodness is, but they don't have a lot of practical use, which is where the Bellman equations come in. These represent our value functions recursively, which allows us to evaluate policies. Whereas the original functions are theoretical constructs that define goodness, the Bellman equations are directly used in reinforcement learning algorithms and show this recursive relationship between our functions. So showing us how good future rewards will be for taking a particular action, or future rewards will be for being in a particular state. And we can use these to define optimality. Optimality is simply a function that outputs the best given state, or the best given action, given a particular state. This is what we seek to learn. We don't actually know what these functions are, but value-based reinforcement learning seeks to learn what these functions are, specifically the Q function. If we were to know the Q function, we could simply have a policy like this, where the policy always outputs the best action, and we could learn something like it with a simple iteration like this. But we don't know our Q function, and in policy-based reinforcement learning, we're not trying to learn that Q function. So how are we supposed to understand how to optimize rewards if we don't know what the best reward is? Well, we do something called Monte Carlo sampling. This is taking a bunch of different trajectories, completing these episodes, in this case, an n number of episodes, and averaging them out to get a more accurate estimate for our cumulative reward. We don't have to compute any of our value functions here. In fact, we don't actually have to know how good our individual actions are in this case. All we do know here is the approximation of our cumulative discounted reward. We can rely on Monte Carlo to make that estimate for us. This is where we can get into policy gradients. We're not trying to learn our value functions, but instead we are trying to optimize our policy directly. In order to do that, let's rethink policies here. Instead of a policy just being a direct map of a state to an action, we are going to have a probability distribution of actions outputted, which we could represent like this by parameterizing our policy. Now, theta, in this case, pi sub theta, represents the parameters, so different values that we can tweak in order to have our agent act differently. P sub theta is the probability distribution given these the policies. And this distribution can be either discrete or continuous in nature. So in some instances, you'll see that you get a vector of different actions that all sum to 1 in terms of their probability. Or you could get like a Gaussian distribution where you're outputted a mean and a variance. But in this case, we're going to focus on the discrete output, just for simplicity's sake. Now that we have that out of the way, we can focus on the actual objective of policy gradient methods. We're trying to maximize our expected reward over a given trajectory. Simple enough. So let's expand this out. So our estimation is going to be the sum of their trajectories given a policy multiplied by our expected reward over that trajectory. Policy gradient theorem states that the derivative of the expected reward is the expectation of the product of the reward and the gradient of the log of the policy. Put more simply, how have our parameters affected the expected return, and how do we get closer to the optimal parameters for the optimal policy? By nature of Markov decision processes, we know that there is an optimal policy out there, which is why we're trying to learn it directly. So in order to do this, we need to take the gradient of our expected rewards, the gradient over the parameters. This will tell us how our individual parameters are affecting our reward and in which direction they're going in order to converge on the optimal policy. And we derive this using the log likelihood trick. This just allows us to, or log derivative trick rather, to get the log likelihood. This is just a implementation of chain rule, which will give us this. Log likelihood makes gradient computation easier, but it also makes stochastic policies convenient to compute the gradients of their parameters for. It certainly helps significantly if we're planning on using this in a sort of algorithm. Next, we're going to decompose our probability distribution, take the logarithm of it, and then take the gradient of it. You'll note that the product is turned into a sum, and you'll also note that we're not including the initial state of our environments or any environmental behaviors, because the policy itself only affects how the agent acts. It doesn't affect anything regarding the environment, and so upon taking these derivatives, those values will be nixed completely as if they're constants. So at the end of it all, we are left with what we have at the bottom here. So to review, trajectories are sampled from the current policy. The log likelihood computes how the policy's parameters are influencing the likelihood of each action at every time step. Trajectories that have higher total returns are weighted higher in the gradient computation, which reinforces actions that lead to successful outcomes. And all of this is aggregated of every actions in the trajectory, which ensures that every single time step is accounted for. So in the reinforce method, these trajectories are going to be sampled using the Monte Carlo method, and we are going to get the mean of their total returns. It is not time dependent, and so we're assigning the same total to every action regardless of when it occurs, meaning that we don't need to know anything about our value functions. And through this, we can finally define the algorithm itself, which looks like this. First, we initialize our parameters arbitrarily, and we initialize our learning rate, which is alpha. And for each sample trajectory, we update our policy based on the gradient that we get from it. You'll notice that this doesn't have an end. We do this until we eventually converge on a optimal policy. We don't know what the optimal policy is, but we can find it eventually. The benefit of this algorithm is that it doesn't require us to know anything about the individual probabilities of our actions or the environment dynamics, and so we have a fully model-free algorithm. We're directly sampling and averaging large sets of trajectory, which avoids the use of any value functions, and the use of G sub t helps us optimize the reinforcement learning objective by introducing the discount factor. So our objective, again, like in the Bellman equations, is likelihood maximization. So this makes it incredibly versatile. It can adapt to stochasticity, and again, you don't need a state or action value function to be estimated. The problem here is that there is a lot of variance that comes from Monte Carlo sampling without any sort of critic, and it's very inefficient. You're consistently over and over again iterating on a policy with no external corrections. And there are many ways to actually improve upon this. So the first offshoot to sort of exist was the reinforces baseline, which is typically a hypothetical value function. Then there's actor-critic learning methods, which is our first visual use of deep reinforcement learning. This uses a calculated advantage that uses a neural net in order to estimate a value function and compare that with the estimated cumulative rewards. Advantage actor-critic, which differs from this since it uses distributed learning using parallel workers or threads to learn these value functions or these critics at the same time as updating the policy. Then there's DDPG, deep deterministic policy gradient methods, which extend to continuous action spaces, and they use deterministic policies rather than probabilistic ones. And these would not have been possible to create without the introduction of the reinforce algorithm itself. It is the, no pun intended, the baseline for all policy-based deep reinforcement learning methods, and it is incredibly important to understand this baseline if you want to do something with policy-based methods. Again, these methods are used for a lot of continuous spaces that don't have any information about their environment. It's model-free. So robotic applications, autonomous driving, things like that. It is a very elegant algorithm, and it is a lot of fun to learn. Thank you.